Hello, can you hear me?
Yes, sir.
Okay, fine. So we'll start now. Actually, uh, I sent I sent handout number 1 and 2. Okay, so with that, our syllabus is over. Okay, so now tomorrow I will send a tutorial, and we'll try to finish both handout today itself, so we can finish the syllabus today itself. Uh, we need some more time, then we'll think another session. Okay. So you all see my screen also, no? Do you see my screen? Hello, do you see my screen? Hello.
Yes, sir.
Right. Okay. So you have to respond. Otherwise, it is very difficult for me to uh, follow you. Right. So in the last class, actually we studied finite Fourier transform. So actually we studied finite Fourier series, finite Fourier series. So I explained these concepts in the yesterday's class, and I have uploaded all the videos, not the videos recordings. So I think I already send you the link for the folder, and I think some of you asked me to share it again, so I will send it tonight. Okay. So I have uploaded yesterday's and day before yesterday also, right? Okay. Now, here in a finite Fourier, normally we know that, let me explain here. Normally, if the range is minus infinity to plus infinity, okay, x is plus infinity, then uh, we use Fourier Fourier sorry, sorry. Then we have the Fourier uh, integral representation. Okay, Fourier integral representation in a complete form. You all know this one. Then this is the first one. Second one, if the range is like this, x is between 0 and plus infinity, then we have two options. One is Fourier sine integral representation. The second one is Fourier cosine integral representation. Okay, so these are about the integral representation. That means that you can represent a function as a Fourier in a Fourier integral form. Okay, so there are two here. The range is like this one. Okay, from this one, we developed. So this is actually Fourier integral representation. This is actually integral representation. Okay, this is actually integral representation. Then using this integral representation, we developed Fourier transform. Okay. We developed Fourier transform. So from this one actually, we had the Fourier complex transform. From these two, okay, we had the Fourier sine transform, and here we had the Fourier cosine transform. Fourier cosine transform. Okay, So this is the outline of the thing. So initially we define integral representation of a function. The range is minus infinity to plus infinity. Then we have the Fourier integral representation. That is the complete form. Using this one, we can define the Fourier transform. This is called the Fourier complex transform. If the range is 0 to infinity, then we have two types of integral representation. The first one we call it as the Fourier sine integral representation, and the second one we call it as the Fourier cosine integral representation. Using the Fourier sine integral representation, we can define Fourier sine transform, and using the Fourier cosine integral representation, we can define Fourier cosine transform. We all know the notations. So now if you look at the range of x, actually here it is minus infinity to plus infinity. Here also it is 0 to infinity. So in both cases, actually the range is infinite. Okay, this is called the infinite range. Minus infinity to plus infinity is also infinite. 0 to infinity is also infinite. So here our range is infinite. Now we have a situation that our range is like this: c less than x less than c plus 2l situation. Now this is actually finite range. This is actually finite. So in this case, this is finite. My mouse is not writing properly. This is finite. So in this case, okay, instead of doing the integral representation, we do the series representation. We have the series representation. Okay, here in the case of infinite thing, we have the integral representation because we are using the integration to represent a function. In the case of finite range, we are using the series representation. So you have to understand the difference. So series representation, okay, series representation. How do we do the series representation? A function we can represent by this form: fx is equal to, it has to satisfy those three conditions. Okay, assume that a function satisfy those three conditions. What are the conditions? Function is periodic with period 2l. Also fx and f dash x both are piecewise continuous. So if those conditions are satisfied, then we can represent this function in the form. So this is called the finite case. This is called a finite case. So in this case, you can express the function in this form: a naught by 2 plus summation an cos n pi x over L plus bn sin n pi x over L. Okay, where n is from 1 up to infinity. So here we are, when the range is finite, we are having a series representation. Okay, so this is called the Fourier series. We call it the Fourier series. Now, if the range is like this, if the range is 0 to L, actually this is full form: c less than x less than c plus 2l. This is full form. Here this is actually half. Actually that is half. So in this case, we have fx, sorry, we have two types of things. One we call it as the sine series, Fourier sine series. Second one, we have the cosine series. So how do we write the Fourier sine series? We write fx is as equal to summation bn sine n pi x over L. N pi x over L. Okay, where n is equal to 1 up to infinity. Cosine series, we write it as the fx equal a naught by 2 plus summation an cos n phi x over 2. Okay, where n is equal to 1 up to infinity. So similar to this one, here also there are three cases: minus infinity to plus infinity. We have the complete Fourier integral representation. The range is 0 to infinity. Then we have two. One is the Fourier sine integral representation. The other one is the Fourier cosine integral representation. Similarly, the range is full. Then we have the Fourier series representation. The range is half. Then we have two types of things. One is the sine series representation. The other one is the cosine series representation. Here, function need not to be odd or even. Okay, we don't want that condition. Okay, we don't want that condition. Okay, there are some more theories. I'm not discussing those theories. If you just know the formula, that is enough. Okay, so using this one, actually, what we can do here, we are having the Fourier transform using the integral representation. We are having the Fourier transform. Similarly, using this series representation, we can have the finite Fourier transform. This is the infinite case, and here we have the finite thing. Therefore, using this series representation, what we can have is so we have the Fourier series representation. Using this Fourier representation, okay, finite Fourier series, Fourier representation, we can have finite Fourier transform. Okay, similar to this one. Using the integral representation, you are having three types of Fourier transform. Similarly, using the Fourier series representation, you can define finite Fourier transform. Finite Fourier transform. Here, you have to note this one carefully. Here, if you look at here, we have actually three types of transformation. One is the complex transformation. We have the sine transformation. We have the cosine transformation. In the case of finite one, we have only two types of transformation. We have only two types of transformation. That is finite Fourier sine transform. Second one, we have the finite Fourier cosine. So in finite case, we have actually only two types. But here, look at here. In the case of infinite, we have three. One is the complex one. The other one is the sine one. Other one is the cosine one. But in the case of finite one, we have only two. What are they? Finite Fourier sine transform, finite Fourier cosine transform. So now we want to study these two. Okay, because already we have completed this one, right? Right. So this is the outline of what we are currently studying. Okay, this is the outline of what we are currently studying. So if we complete these two, then we can go for application. So if we finish the application, with that we can finish it. So you can remember, once we studied this, we had one more thing that is called the Parseval identity. You can remember that one. So once we studied this, here we studied Parseval identity. Similarly, now we are here. Now we are at this point. Okay, now we are at this point. Now we have something called the Parseval identity for finite case. For finite case. Okay, we have Parseval identity here. After we studied this integral transform, after we studying integral transform, we actually had the Parseval identity. Okay, then we studied Fourier transform. Similarly, here also we have completed studying Fourier series representation when the range is C in the form C plus 2L. when the range is half range, that is 0 to L, then we have the sine series and the cosine series. Then now we are here. We want to study Parseval identity for finite case. After that, if we study finite Fourier sine transform and finite Fourier cosine transform, then, and if you study the application, actually application is solving PDEs, then our syllabus is solved. So this is the outline. Okay. So later I will prepare a summary sheet because there are so many formula. Therefore, I will prepare a summary sheet and send it to you. Okay. Right. So now we'll go to our handout. Right. So did you try this question? I gave you homework. Did you try this example number 2? How many of you tried this one? How many of you tried this example number 2? And have you got these answers? Hello? How many of you got this answer? Anybody got these answers? Please respond. Otherwise, now, we are taking, it is taking a lot of time since you are not responding quickly. That is why we are so late. How many of you got this answer? At least one? Anybody got the answer for this question? Answer for this homework? No one got the answer. There are 80 students. At least one of you didn't get the answer. Anybody got the answer for this question? Were you able to show these things? Or you want me to discuss? Hello? Can you listen to me? Anybody got the answer for these questions? Tell me whether you got answer for these questions. Hello? Need discussion. Why you didn't try this? Yesterday I explained clearly, no? So when I asked, you said understood. Now you all are asking discussion. You don't understand the reason. Okay, anyway, we'll discuss. Then don't blame me, okay? For being late. Okay, now the function is fx is equal to x square. The range is minus pi, x is less than plus pi. Okay, plus pi. So actually here in this question they are asking us to obtain a Fourier series. Okay, neither cosine nor sine. So clearly they are saying that our Fourier series. Therefore, we have to get the complete one. So this is our C. This is our C. This is our C plus 2L. So from this one, you can find out L. So can anybody tell me the value of L? What is the value of L then? What is the value of L? Pi. The value of L is equal to pi. So first of all, actually we know that fx is equal to a naught by 2 plus summation an cos n pi x over L plus bn sin n pi x over L. This L is inside this angle. Huh? You have to understand that one. Otherwise, you will make mistake. Okay. Right. So n is running from 1 up to infinity. So first of all, they are asking us to find the Fourier series of this function. So we'll find one by one. So we'll first find a naught. So a naught, according to the definition, a naught is equal to 1 over L. So our L is equal to pi. So 1 over L means 1 over pi integration minus pi to plus pi. I'm just using the definition. Okay, I'm using the way it is defined. Minus infinity to fx dx. Fx is x squared into dx. So this is equal to 1 over pi. Please let me know if I make any mistake. This is equal to x cube by 3 minus pi to plus pi. Then if you substitute value, you will get 1 over pi. Then we get pi cube by 3 minus pi cube by 3. So that becomes plus pi cube by 3. So that is equal to 2 pi squared by 3. If you simplify this one, that becomes 2 pi squared by 3. So A naught is found. A naught is found. A naught is found. Then we want to find AN. So how AN is defined? 1 over pi integration minus pi to pi. Okay, fx is equal to x squared into cos n pi x over pi. L is equal to pi into dx. So pi get cancelled. So that is equal to 1 over pi minus pi to plus pi x squared into cos nx dx. So actually you have to use integration by parts method. So that is equal to 1 over pi. Okay, so if you if you put x squared into an integration of this one. So what is the integration of cos nx? Can anybody tell me what is the integration of cos nx? That is sine nx by n. Sine nx by n minus derivative of this one. So derivative of this one is 2x into integration of this one. So what is the integration of sine nx over n? So that is minus cos nx over, already we have n, so that becomes n square, plus integration of this one is 2 into differentiation of 2x is 2 into integration of this one is equal to integration of cos is equal to sine nx over, already we have n, so that is n cube, but we have minus. So we have to substitute minus pi to plus pi. Minus pi to plus pi. So what is this? Can anybody tell me? What is the answer of this one? It's equal to 1 over pi into, if you put, if you put x equal pi, okay, x equal pi, x equal minus pi, in all cases, this becomes 0. Because sine pi x is equal to 0. This also becomes 0. Okay. So what we have is minus into minus is plus. So plus. So minus into minus is plus. So we have 2x. So if you put substitute 2x, then we get 2 pi over n squared 2 pi over n squared. 2 pi over n squared. Here cos n pi. Cos n pi is, can anybody tell me what is the value of cos n pi? What's the value of cos n pi? Yesterday I told you. What's the value of cos n pi? What is the value of cos n pi? Not minus 1. Not minus 1. N pi means if n is equal to 1, then it is minus 1. If n is equal to 2, cos 2 pi is actually what? Plus 1, isn't it? Cos 2 pi is equal to plus 1. Just, you know, you don't need to memorize these things. You can just draw and see. Okay, so this is the cos curve. So here, this is the cos 1 pi. Actually, this is the cos 2 pi. Okay, and so on. Therefore, cos n pi is equal to minus 1 to the power n. Minus 1 to the power n. Therefore, here, if you put that one, we get minus 1 to the power n minus, then if you put minus pi, then this becomes plus 2 pi, again, minus 1 to the power n over n square. Over n square. Okay. So then if you simplify this, we get pi get cancelled. So we can get 2. So we can get 4. 4 minus 1 to the power n over n square. Am I correct? Tell me whether I am correct or not. Is this correct? Tell me whether this is correct or not. Anyway, check the answer. Do you understand why this became 0? Because if you substitute pi, cos n pi is equal to 0. Even if you substitute minus pi, that time also it is 0. Therefore, sine terms become 0 when you substitute pi, even minus pi. So this is the answer. Similarly, we have to find bn. So bn is equal to, similarly, 1 over 5 integration minus pi to plus pi. We have x squared into sine n x, because here also pi, here also L is equal to pi. Therefore, this becomes this way. So, can you tell me the answer of this one? Can you tell me the answer of this one? Can anybody tell me the answer of this one? You don't need much calculation this time. So, actually, x squared is a even function. X squared is a even function. Sin nx is odd function. Sin nx is odd function. So, ultimately, this is an odd function. So, what is the integration of odd function? Minus a to a fx dx. Can you tell me what is that function? What is the value of this function? If it is odd function, f is odd. That is 0. So that is 0. So you can just say that this is equal to 0. The reason is x squared into sin nx is an odd function. Okay, so we have found an, a naught, and an. Now we are able to write fx. So our fx is equal to, actually our fx is equal to x squared plus a naught by 2. Sorry, it's not x squared plus. Our fx is equal to x squared, which is equal to a naught by 2. What is my a naught? 2 pi squared by 3. So by 2 mean pi squared by 3, isn't it? Pi squared by 3 plus summation n equal 1 up to infinity. Summation n equal 1 up to infinity. My an is equal to 4 times minus 1 to the power n over n squared into cos n pi x over L. My L is equal to pi, therefore I will get nx. So that is the Fourier series of x squared. Okay, because my Bn is 0. Now, if you look at the question, first one is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared equal to this one. So what is the suitable value if you put for x? What is the suitable value you can put for x? Can anybody tell me what is the suitable value that we can put for x? So you have to think this time. Now, can anybody tell me what is the suitable value that you can put for x so that you can get this one? So that you can get this one. Look at here, all are positive. All are positive. So so here we have minus 1 to the power n. So what is the suitable value that we can put for x so that we will all the terms will be positive? Can anybody tell me? Can anybody tell me what is the value? Think and tell me. Actually, now if you look at this function, okay, this is actually minus pi to x this pi, but actually it is periodic function. Actually, x squared is not a periodic function, but if you draw this one, meaning is that it is extensible, periodically extendable. So it is like this. Okay. So that is the meaning. That is the meaning of this one. Periodically extendable. Okay, periodically extendable. So what is the suitable value that you can put for put for x so that you can get this one? So here this is pi. Okay, this is pi. So this is pi. Again, this is minus pi. So this is 3 pi, and so on. It goes in that way. So that is the meaning, because actually x squared is not a periodic function. So they have given that x squared is between minus pi to mean it is extendable. Extendable mean here they have given only for this range. Here they have given only for this range. So meaning that it can be extended so that it is periodic. So now I am asking, okay, actually now I am asking what is the suitable value you can put for x so that you can get that series. Think and tell me quickly. We want to move to next one. At least one of you. At least one of you can't tell me. So think, if you put x equal pi, what will happen? Left hand side, pi square is equal to pi square by 3 plus, you can take 4 out, summation n equal 1 up to infinity minus 1 to the power n over n squared into, again, cos n pi. What is cos n pi? Minus 1 to the power n. So what is this actually? So if you simplify this one, when you bring this to this side, we get 2 pi squared by 3, no? 2 pi squared by 3. And if you divide by 4, then you will get pi squared by 12. Just I'm simplifying. Okay, I'm bringing this pi squared by 3 this side and dividing by this 4. Then I will get pi squared by 12. Pi squared by 12, but already I have 2 here. Therefore, I will get pi squared by 6. I'm sorry. Equal summation minus 1 to the power n into minus 1 to the power n. What is that? Minus 1 to the power 2n over n square. Can anybody tell me what is minus 1 to the power n square? What is the value of this one? That is 1, because this is an even number. 2n is anyway even. Therefore, this is 1. So we are getting pi squared by 6 is equal to summation 1 over n square. So what is that? 1 over 1 squared plus 1 over 2 squared. So that is what we are having here. Pi squared by 6. Do you understand? Do you understand, students? Hello? Do you understand this? Right. Now I am asking the second one. This time you have to tell me. So what will be the suitable value that you can put for x this time? Using the same one. Using the same expression. If you want to now look at the series carefully, you have to observe the series and then you have to pick the suitable value for x so that you will get this series. Now here, actually plus and minus are altering. Okay, first one is minus, then plus, then minus, and it goes like that. So now what could be the suitable value for x so that you will get that one? Tell me now. Now you have some idea. So what is the suitable value that you can put for x? Tell me x equal to. Yes, tell me what is the value of x that you can put so that you can get the second series. Minus pi. No, minus pi will not work. Why minus pi will not work? Because even here, look at the series. This is cos n pi x, no? So cos minus pi is again minus 1 to the power n. So you will get the same one. You will get the same one. 3 pi. Not 3 pi. 3 pi also will not work. So what is the 3 pi? 3 pi mean what? 3n pi. 3n pi is again minus 1 to the power n. Yes, 0 is the suitable value. If you put 0, okay, so cos 0 is 1. Here look at minus 1 to the power n mean first one is minus, then plus, and it will go like that. No? So if you put x equals 0, then this side we will have 0 square equal, okay, we have pi squared by 3 plus 4 times summation minus 1 to the power n over n squared into cos 0 is 1. So now what we are having is here, when we come to this side, this is minus pi squared by 12 equal. Now if you put n equal 1, we get minus 1 over 1 squared, n equal 2 plus 1 over 2 squared minus 1 over 3 squared and so on. So if you multiply by minus, then you will get pi squared by 12 equal to 1 over 1 squared. So you are multiplying by minus both sides. So then you will get minus 1 over 2 squared, then plus 1 over 3 squared, and so on. You understand? So then we are getting pi squared by 12. Do you understand? Tell me whether you understood or not. So using the same series, you have to identify the suitable value for x so that you can get the series. So that is the idea. That is the idea. What about others? Only if you are responding. What about others? Do you understand? Right. Fine. Now, how we can get third one? Can anybody tell me? We can directly get the third one. Yesterday also I told you. How we can get the third one? Just observe the third series. Do we have to substitute any value for x, or we can easily get it? Can anybody tell me how we can get the third series? How we can prove the third one? Yeah, if you add 1 and 2, if you simply add 1 and 2, you will get the third one. Okay, so you have to think. You have to think. Yesterday also I worked out this problem and show you that when you put x equals 0, we'll get this one. Okay, right. Now let's talk about the Parseval identity. Okay, actually, proof is not necessary. It says that we know that the Fourier series expansion is like this. Okay, we are familiar with this one. Okay, here we are having the range from minus L to plus L. So minus L to plus L means our C is equal to minus L. Okay, our C plus 2L is equal to L. So that is that our L is equal to L. So our period is 2 pi. Okay, so here, so we are given this way. So from this one, you have to understand that period is 2 pi. 2L, sorry, 2L. Okay, so in that case, it says that 1 over L minus L to L fx squared. 1 over L minus L to L fx squared equal to 1/2 a naught squared summation an squared plus bn squared. So this is the Parseval identity for finite case. We have only one. We have only one. Okay, so very simple. If this is the Fourier series expansion of the function fx, then the integration minus L to L fx squared 1 over L into integration minus fx over minus L to L, not fx squared dx is equal to, it is actually equal to half times a naught squared plus an squared plus bn squared. Okay, so this is one of the interesting and important one. Okay, definitely you will get a question on this one. Okay, you must know this Parseval identity. If we ask you to state You don't need to prove it. If you ask you to prove this, sorry, not state this, you should be able to state this one. Okay, here you have to mention this also. You have to carefully mention this also. Otherwise, this is applicable when the range of x is minus l to plus l. Okay, so now let's work out this problem. Example number 4. Example number 4, and find the Fourier series representation. Okay, find the Fourier series representation of fx where fx is equal to mod x minus 2 to x. Deduce that this one. Now we will work out this one. So right. So our function fx is equal to mod x. Function fx is equal to mod x, where the range is minus 2 to plus 2. Okay. First of all, they are asking us to find a Fourier series expansion of this one. So we want to find out A naught. So A naught is equal to, according to the definition. Actually, what is the period? Can anybody tell me what is the value of L here? Can anybody tell me what is the value of L here? Yes, L is equal to 2. L is equal to 2. L is equal to 2. What is the period? Period is equal to what? That is 4. Period is 4. Right, good. So A naught is equal to, according to the definition, 1 over L. So 1 over L means 1 over 2 minus 2 to plus 2. Our function is mod x. Okay, mod x into dx. So can anybody tell me the answer of this one? Can anybody tell me the answer of this one? Half times minus so how to evaluate this one? This is equal to half times. Actually, we have to split the interval. Minus 2 to plus 2. So in the, sorry, minus 2 to 0. Sorry. Minus 2 to 0. The function is minus x. Okay, because in the negative side, the function is, we know the absolute value function definition. You all are familiar with that, no? So mod of x is equal to what? X, if x is greater than or equal to 0, minus x if x is less than 0. So using that one, in the range minus 2 to 0, it is x plus 0 to 2 x dx. So if we will evaluate, so this is equal to half times, and if you take minus out, this becomes x squared by 2. We have to put minus 2 to 0 plus this one is also x squared by 2. We have to put 0 to 2. Remember, there is half out. So that is equal to half times. So if you put 0, minus is there. If you put 0, 0. If you put minus 2, then that is plus 4. Then that becomes plus 2. No? Plus 2 plus Here, if you put x equal 4, then that is become 2. I'm sorry, this should be minus, no? So 2 minus 0. So this is equal to minus into minus is plus, plus 2 is 4. 4 divided by 2 is equal to 2. So A naught is equal to 2. A naught is equal to 2. Now we want to find out AN. So AN is equal to 1 over 2. L is 2. Integration minus 2 to plus 2. Minus 2 to plus 2. Mod of x into cos n pi x over L. Our L is 2. So this is equal to half times. Like earlier, we have to split the interval. So that becomes minus 2 to 0 minus x. So I'm taking that minus out. Cos n pi x by 2 dx plus integration 0 to 2. In that range, it is x cos n pi x by 2. Okay. So now we have to do the integration. Half times. So first one, if you integrate, what is the first integration? So minus is there. First function is x into integration of this one. So integration of this one is what? Integration of cos is, we know that sine, no? Sine n pi x by 2. Okay. Into 2 over n pi. 2 over n pi minus integration of x is, sorry, differentiation of x is 1. 1 into integration of this one. So integration of this one is actually minus cos. Minus cos x pi by 2 into 2 means 4 n squared pi squared. Okay, the range is minus 2 to minus 2 to 0. So this is for this one. Okay, so this one is for this one. And similarly, we have to do for this one. So the same integration, but here we have plus. So that becomes, let me write it in different color so that you can easily identify. Plus the same integration, that is x into sine n pi x by 2 into, sorry, into 2 over n pi minus 1 into minus cos n pi x by 2 into integration of that one is again 4 over n squared pi squared. Here again we have to put 0 to 2. So now we want to evaluate this one. So if you put, so that is equal to, if you put actually first one, if you evaluate the first one, if you put x equals 0, this part becomes 0, this part becomes 0. Here minus into minus is become plus, and if you put x equals 0, this becomes 1. Therefore, we get, but already we have minus here. Therefore, we get, so I'm writing here minus. Now I am substituting x equals 0. Then this becomes 4 over n squared pi squared. Now, if I substitute n equal minus 2, if I substitute n equal minus 2, sorry, x equal minus 2, then this becomes cos n phi. So cos n phi mean, because x minus 2 get cancelled, x equal 2, and these two get cancelled, so that becomes 0. So this part is going to be 0. When I substitute x equal minus 2 here, x equal minus 2 here, that minus 2 get cancelled with this one. This is a cos function, therefore minus is not a problem. Therefore we get cos n phi. But here it is minus into minus is plus. Therefore I will get minus 4 over n squared pi squared. Cos n phi is equal to minus 1 to the power n. Minus 1 to the power n. Please try this one, okay? Minus 1 to the power n. Minus 1 to the power n. Then plus. Similarly here also, when you substitute x equal 2, you substitute x equal 2, this part becomes 0, this part becomes 0. Here minus into minus is plus, here minus into minus is plus. Then this becomes, here it becomes 4 into minus 1 to the power n over n squared pi squared. And if you substitute 0, then that becomes minus 4 over n squared pi squared. Okay, right. Now I have a minus here. Look at here, minus 4 over n squared pi squared, minus 4 n squared pi squared. Minus into minus is plus. Both are same. Look at here carefully. This term and this term both are same. Okay. Similarly, this term and this term both are same. But minus, so ultimately it is reduced to 4 means 8. 8 into minus 1 to the power n over n squared phi squared, n squared phi squared, minus 4, that becomes 8 over n squared phi squared. So I can simplify this. I can take 8 over n squared phi squared out. I'm sorry, I have a half also. No, I have forgot to put that half also. There's a half here. Therefore, there will be a half here. Then this becomes 4. So that becomes 4. 4 over n squared pi squared into minus 1 to the power n minus 1. Okay, minus 1 to the power n. You have to do simplification. That is very important. Now an is found. Bn is equal to, similarly, 1 over 2 into minus 2 plus 2 mod of x into sine n phi x by 2. Can anybody tell me the value of this one? What is the value of this one? and reason. Quickly, it is 0. Why it is 0? Because mod x is an even function. So even function, so sine is odd function, so ultimately it's an odd function. Therefore, that is 0. So Bn is 0. Therefore, now we have that our fx is equal to, now we can write this series expansion. Mod of x is equal to, mod of x is equal to, we have our an, no? So our a naught is equal to what? 2. Therefore, a naught by 2. A naught by 2 means 1 plus summation n equal 1 up to infinity. Our an is equal to what? 4 times, no? So 4 over n squared. So I can take that 4 over pi squared out. 4 over pi squared out. Then I have minus 1 to the power n minus 1 over n squared into cos n phi x by 2. My L is 2. Okay, so that is the series expansion. Now, actually, here, if you look at the question, actually, it is 1 to the power 4, 3 to the power 4, 5 to the power 4. Here, what we are having is n squared. N squared. Therefore, how we can get something to the power 4? Something to the power 4. So that is our concern. That is our concern. Therefore, now what we can do is we can use the Parseval identity. So Parseval identity says what? 1 over L minus L to L fx squared dx is equal to half times a naught squared plus summation an squared plus bn squared. So in order to get this one, we will use the Parseval identity. In the examination, normally we will give a clue, because you first question may be asking state the Parseval identity, and second question may be deduce this one. So then you will be able to do that one. Okay, so here sometime if you become expert, then you can get some idea. Therefore, Parseval identity says what? So now I am using the Parseval identity. Using the Parseval identity, I can write 1 over L, no? So look at the Parseval identity, 1 over L. So 1 over L means 1 over 2 minus 2 to plus 2 mod of x fx squared. Mod of x squared is equal to, it says that half times a naught squared plus summation n equal 1 up to infinity an squared, because my bn is 0. The reason is bn equals 0. Isn't it? bn was 0. bn was 0. Therefore, I can write this way, n up to infinity. Now, I want to find out this one. So, this implies is half times. Okay. So, this one is what? Mod of x squared means it is x squared. No problem. Mod of x squared means it is x squared. Therefore, if I integrate that one, I get x to the power 3 over 3 minus 2 to plus 3 equal half times my a naught is equal to 2. Therefore, a naught squared is equal to 4 plus summation n equal to 1 up to infinity. My an is equal to what? My an is equal to, look at my an, this one. So squared mean what? 16. Square of this one. So 16, look at here. 16 n to the power 4 pi to the power 4. Into square of this one. minus 1 to the power n minus 1. So look at here. So minus 1 to the power n minus 1 square. Okay, no cos or anything. Because Parseval identity, look at the Parseval identity. There is no cos or anything. Only square of the coefficients. Only square of the coefficient. Don't get confused. Don't get confused. Okay. So then we get this one. So what is the answer of this one? Half times. So if you substitute this one, we get 8 by 3 minus 8 by 3. So therefore plus 8 by 3. So which is equal to 8 by 3. 8 by 3 means we have 16 by 3. 16 by 3 means if you divide by this one, 8 by 3. No? 8 by 3 equal, and right hand side, if you simplify this, we get 2, and you can take it out 16 over 5 to the power 4. 16 over 5 to the power 4. And if you write the series, say for an example, if you put x equal 1, sorry, n equal 1, if you put n equal 1, then what is the answer of this one? Minus 1, that is minus 2. Minus 2 to the power squared. Minus 2 to the power squared means we get 4 over 1 to the power 4. If you put n equal 2, that is 0. We get plus 0 over 2 to the power 4. Plus, if you put n equal 3, then again it is minus 1. Minus into minus is plus. So that is 4 over 3 to the power 4. If you put n equal 4, then that is 0 over 4 to the power 4, and so on. Okay. So if you further simplify this, if you subtract this one, minus 2 this side, 8 by 3 minus 2 means 1 over 3. 1 over 3. And if you multiply that one, we get 5 by 4. Yeah. That is 1 over 3, no? So we get 1 over 3 means 2 over 3. So 2 over 3 means 2 over 3 means we get 5 by 24. Here you can take 4 out, and if you omit the 0 terms, you get 1 over 4 plus 1 over 3 over 4 plus. Okay, so from this one you can say that 1 over 1 4 plus 1 over 3 over 4 plus so on is equal to 5 by 5 to the 5 raised to the power of 4 divided by 96. Okay, same as this one. Do you understand this one? Tell me whether you understand or not. Quickly tell me now. Time, we are running out of time. I thought of finishing this today. Now it is 9:30 almost. So how can I finish this today? What about others? Do you understand how I got this one? So actually, you have to do some work here. Also, look at here. I didn't calculate Bn because using the idea of odd function, even function, you can save some time. You can save some time. Look at here. So those idea always should be in your mind. Those idea always should be in your mind. Okay, right. So that is all about the Parseval idea. Now we'll move to the last thing, that is Fourier, finite Fourier sine and finite Fourier cosine transform. Okay, as I told you earlier, look at here. I go to the outline again. Here we had the integral representation, and then we had 3 types of transformation. When you come to the finite case, here also we have 3 types of series representation. One is the full form. The second one is the half range. Half range is when the range of x is 0 to L, we have the sine series in this form and cosine series in this form. Now, like here, using the integral representation, we are defining the Fourier transform. Here we have 3 types. But fortunately, in the case of Fourier series representation, we have only two types of finite Fourier transform. One we call it as the finite Fourier sine transform, finite Fourier cosine transform. We don't have finite Fourier transform. We don't have finite Fourier transform. We have only finite Fourier sine transform and finite Fourier cosine transform. Here we have three: finite Fourier complex transform, Fourier sine transform, Fourier cosine transform. Here we are having three. But in here, actually, we have only two. Only finite Fourier sine transform, finite Fourier cosine transform. Okay. So in that case, actually, our interval must be 0 to L. Because we are actually defining from the sine series representation and cosine series representation. No? In order to write the sine series representation and cosine series representation, actually our range should be 0 to L. Therefore, we define finite Fourier sine transform and finite Fourier cosine transform for the range 0 to L. Okay, so that is why now we are going to talk about. Okay, that is why now we are going to talk about. Right. Now we'll talk about finite Fourier transform. Actually, here we have two. One is the finite Fourier sine transform. We'll see how it is defined. Now, we have a function. The range of, we have a function fx. Okay, let me write it here. It's a common one, no? So let me write it here. We have a function fx. The range is this one. Okay, this is very important because we are going to define finite Fourier sine transform and finite Fourier cosine transform. First one, we are going to define finite Fourier sine transform. So it is defined as this way. Okay, f s means sine, same as earlier. Fx, okay, equal. Okay, we are using the notation this one. F bar s. Earlier we put omega. Since it's a finite one, here we are putting n because we are going to have the function in n. It is defined to be, okay, integration 0 to L, okay, fx into sine n pi x over L dx. Okay, dx, because we will get the answer in n. So this is called the finite Fourier sine transform. This is called a finite Fourier sine transform. So how do we identify whether it's finite or infinite? If it is n, then it is finite one. Some people put p for this one. Here also they put p. Here also they put p. Some people put s, but here we are putting n. Okay, don't get confused. So 0 to L, fx sine n pi x over L. Then inverse of this one, inverse is actually fx. Fx is equal to, okay, fx is equal to summation 2 over L, sorry, 2 over L, summation n equal 1 up to infinity, f bar Sn into sine n pi x over L. Okay, so this is the inverse Fourier transform. Inverse finite Fourier sine transform. Okay, so inverse formula is this one. Inverse is given by this one. What do you mean by what is this actually? Actually, what is this? Can anybody tell me what is this? Can anybody tell me what is this? If you can remember, what is this? This is nothing. This is nothing. Fourier. This is actually. This is actually Fourier sine series. So actually, the inverse Fourier transform is nothing but Fourier sine series of the function. Fourier sine series of the function. Look at here. Look at the definition. Okay, this is nothing but Fourier sine series representation of the function. Okay, similarly, okay, if you don't understand the last point, don't worry. Just understand the formula. This is the finite Fourier sine representation, sorry, transform, and this is the corresponding inverse formula. Similarly, we have the second one, that is finite Fourier cosine transform. The function, if it is defined as f c fx, we are denoting it by f bar c n equal integration 0 to L, okay, fx into cos n pi x over L into dx. Inverse Fourier, finite Fourier cosine transform is, sorry, you can put fx equal to, here actually you have to put this note, a naught by 2, okay, plus summation, yeah, you can put a naught by 2, or right, we'll not put a naught by 2, we'll put some other thing, okay. So we'll put fx is equal to, okay, f bar c naught. That means the value at 0, plus summation f bar c n, f bar c n into cos n pi x by L. Okay, n equal 1 or 2. Here actually, this one is, I think half should be there, no? Sorry, 1 over L, I'm sorry. Sorry. I'm sorry. I made a mistake, sorry. Here also we have 2 over L, no? Similarly, here, sorry. Sorry. Yeah. So I'm sorry, here it is 1 over L. Okay, careful about this one. So inverse is 1 over L f dash C naught, where f bar C naught is equal to integration 0 to L fx, okay, fx dx. It is given here. F bar C naught, this one is actually defined with this one. Okay, so these are the definitions. Okay, So you have to by heart, in addition to those things, you have to by heart these 4 things. So we are defining finite Fourier. Actually, we have only 2 finite Fourier transform. One we call it as the finite Fourier sine transform. It is defined in this way, and its inverse is given by this way. Similarly, finite Fourier cosine transform, it is defined to be this way, and its inverse is defined to be this way: 1 over L f bar c naught plus 2 over L into f bar n this one, where if this one is equal to this one. Okay, so that you have to understand. Do you understand up to now? Do you understand the definitions, how it is defined? You don't need to prove these things. If you know this formula, it is enough. Do you understand up to now? Shall we go for some questions? Hello, do you understand? Right. So example number 1. Fx is equal to x. Define x is less than 1. Question number 1. Find finite Fourier sine transform. Second one, finite Fourier cosine transform. Okay, let's work out for this function. So here, if you compare the earlier one, this is our L. Our L is equal to 1. Now, if we look at here, look at the way the function is defined. Actually, our function, the range should be 0 to L, because we are defining sine and cosine transform. Therefore, our range should be this one. So whenever you define the finite Fourier sine and transform, you have to clearly mention all these conditions. You have to mention, given a function fx, where the range of x is 0 to L, then the Fourier sine transform is given by this one. Okay. So it is function of new variable n. N is actually n belongs to natural number. Okay, n belongs to natural number, because here we are defining that way, no, the series form. Therefore, n belongs to natural number. Here also n belongs to natural number. It's a finite one. It's a discrete one. Therefore, we are having n belongs to natural number, right? So these are the definition. Now we will work out this problem. First, we will work out finite Fourier sine transform. So finite Fourier sine transform is what actually? So how it is defined? Finite Fourier sine transform. So we'll define finite Fourier sine transform of x. So which is defined to be f bar. You have to be careful about the notation. Sn equal to integration 0 to L. So 0 to 1. Function is x into sine n pi x over L. L is 1 into dx. Into dx. Okay, into dx. So this is equal to what? So it's a matter of just evaluating this integration. So this is equal to, first function is x into integration of this function. So what is the integration of sine? We have cos n pi x minus, no? Minus cos n pi x. Sorry, one more term should be there. No? Into 1 over n pi 0 to 1. Okay, minus minus integration of this one. Sorry, differentiation of this one, that is 1 into and integration of this one. So integration of this one is actually sine Therefore, but already we have minus. Therefore, minus sine n pi x. So this is just this is not minus. Okay, just dot into sorry n pi x into sorry. Let's utilize the space. So this is equal to 1 into integration of this one minus sine n pi x into 1 over n square pi square. Here I want to put 0 to 1. Okay. Now, if I substitute the value, please check whether I'm doing correctly or not. So, if I substitute the value x equal 1, there's a minus here. Then minus cos n phi is equal to what? Minus 1 to the power n. Minus 1 to the power n. And if I put x equals 0, that is 0, minus 0. Minus, if I put x equal 1, sine n phi is 0. And if I put that part is 0. So I get minus 1 to the power. So that is right, minus 1 to the power plus 1. Okay. So therefore, my finite Fourier sine transform. Finite Fourier sine transform of x is equal to f bar s n is equal to minus 1 to the power. Do you understand this one? Please check this calculations. Okay, I just took this example. I didn't check out this one. Please check this example. Do you understand this one? Tell me whether you understood or not. Hello. Tell me whether you understood or not. Hello. Do you understand this? What about others? Right, fine. So similarly, we will find out the Fourier cosine transform of the same function. So Fourier cosine of x, so which is equal to f bar c n, which is defined to be different way. How it is defined? I'm sorry, I have made a mistake. Can anybody figure out? Ah, okay, that's fine. So it is defined to be what? It is defined to be 0 to L x into cos n phi x into dx. Okay, why? Because my L is equal to 1. My L is equal to 1, no? So there should be 1. Therefore, now if I have to integrate this one, so if I integrate like this one, I will get x into this one is cos. If I integrate cos, that becomes sine n phi x into 1 over n phi. I want to put 0 to 1 minus differentiation of this one is 1 into integration of this one, that is minus cos n phi x into 1 over n phi square. Zero to 1. So if I substitute here sine function, if I substitute 1 sine n phi 0, this is also 0. So this part becomes 0 minus here if I substitute x equal 1, if I substitute x equal 1, yeah, if I substitute x equal 1, then this becomes minus is already there. So this becomes minus 1 to the power n over n squared I squared minus, already there is a minus, therefore this will become plus. When I substitute 0, that is 1. So 1 over n squared pi squared. Check these calculations, okay? So if I multiply by minus completely, and if you take minus 1 over n squared pi squared out, we get n over squared pi squared into minus n pi. Which one is minus n pi? First part, minus 1 to the power n. Which one you are referring to? I didn't get. If you integrate this one cos n pi x, we get sin n pi x, no? So I didn't get which one you are referring to. fs6. fs6. Sorry. Sorry. Yeah, n pi is there. Nah? I'm sorry for that. So there is n pi here. I'm sorry for that. So that n pi will come here. Thank you very much. Thank you. Okay. So similarly here we have any problem. We don't have any problem. So that becomes, if you take minus 1 over n squared pi squared out, then when you multiply this one, we get minus 1 to the power n minus 1. So that is the Fourier cosine, finite Fourier cosine of this one. Okay. So right. So that is over. Now there are some questions here. That is end of this year not. So I couldn't finish this second. I couldn't start this one. So if possible, tomorrow we'll have one more session and we'll finish it. I will tell the time if possible. Now we will work out this one and finish it. Okay, you try the rest of the thing. Okay, you try the rest of the questions. Okay, here the inverse is given. Okay, inverse is given, and we want to find out this one. Okay, right. So we'll if we get time, we'll work out that also. So I just want you to, we'll do the first one. Here, look at A belongs to N. Okay, here A belongs to R. Look at here. The range is 0 to this one. We'll work out this problem and we'll finish it. So sine AX. So we want to find, what's the transformation we want to find? Finite Fourier sine transform. We want to find the finite Fourier sine transform. Our fx is equal to sine AX, where A belongs to set of natural number. X, the range of x is 0 less than 5. Okay, 0 less than 5. So we're going to use the definition. So I'm directly writing that one. Sine of bar n is equal to integration. My L is equal to pi. So 0 to pi, because my L is equal to pi. Okay, sine AX into sine n pi x over n pi x. Sine, this is the one, no? Sine n pi x over L. My L is also pi, so pi get cancelled. So I will get sine nx dx. So how can I integrate this one? Sine ax into sine nx. How can I do this one? A is also natural number. A is also natural number. So A is also natural number. N is also natural number. So how can I simplify this one? Can anybody give me an idea how we can simplify this? 0 to pi. Can anybody give me an idea how we can simplify this? What is the idea? How we can integrate? How we can do the integration? Sine ax into sine nx. Any idea? Yeah, 2 sine a into sine b form. So using the trigonometric one. So how we can write this one? You can write this as half times. Since both are sine, we have cos. No, so I can write this as cos a minus nx minus cos a plus nx. Okay, so this is equal to, I can take half out, 0 to pi. I have this one. Minus into dx, sorry. Plus now there's a problem now. We have a minus n. So here a plus n is not an issue because a is also natural number, n is also natural number. But when a equal n, this part will become 0. Therefore, we have to consider case by case. Case 1, if a not equal to n, sorry, simple error. A not equal to simple n. So if a not equal to simple n, then this integration fs n becomes half times. What is the integration of this one? Can anybody tell me? Half times. What is the integration of cos a minus n over x? It is 1 over a minus n sine a minus n over x minus 1 over a plus n sine the range is 0 to pi. So look at here carefully. If a not equal to n, otherwise this will become infinity. Okay, otherwise this will become infinity. That is why I am doing case by case. If a not equal to infinity, so then this becomes what? If you substitute pi, okay, this is a minus n is also natural number. A minus n is also natural number. A plus n is also natural number because a is a natural number. N is already a natural number because we are working on finite Fourier. Therefore, a is also a natural number. B is also a is also a natural number. Therefore, a minus n is also a natural number. A minus n is also natural number. Natural number means or integer, you can say, and a plus n is also integer. This is clearly natural number because when a is greater than n, sorry, when n is greater than a, sometimes it may be a negative number, no? So we can't say that natural number. So it can be a integer. But whatever the case, both will be 0 because sine pi x is also 0. Sorry, sine k pi is also 0. Sine 0 is also 0. Therefore, this will become 0. This will become 0. Do you understand why it became 0? Because if you substitute 0 also 0, if you substitute pi also, it is 0. Therefore, fsn, if a is not equal to n, becomes 0. If a equal, case number 2, if a equal n, then what will happen here? If a equal n, this will become 0. That means cos 1, cos 0 is 1. Therefore, that integration will become, so this is sine, will become half times integration 0 to pi 1 minus cos a plus n So if you integrate this one, half times x minus 1 over a plus n a plus nx 0 to pi. Okay. So now if you substitute the value, this part becomes 0 because sine pi is also 0, sine 0 is also 0. Therefore, we get half times pi minus 0. So that is equal to. Therefore, now we can say that the finite Fourier sine of, you can say that finite Fourier sine equal f bar s n. Here are two solutions. One is pi by 2 if a equal n 0. Do you understand this? Hello, do you understand? Hello, do you understand? Tell me whether you understand or not. What about others? So you have to be familiar with the trigonometric identities. You have to be familiar with odd function, even function, integration by parts, and so many things you have to be familiar with. Now I will tell you a few more things. Look at here. So I'll give you one clue here. Say for an example, this is integration by parts. Say you have to do integration uv dx. There are two functions. U is one function, b is another function. So you can continuously do the integration. How? Wait a minute. You can say that u into v1 minus u dash into v2 plus, this is what I really did, u double dash into v3 minus, plus minus will alter. Okay, u triple dash into v4 and so on. So where u dash comma u double dash, these are derivative, consecutive derivative of u. v1 is what? v1 is integration of v. v2 is what? Integration of v1. v3 is what? Integration of v2 and so on. Okay, so you can actually, this is a very useful thing. You can extend for any number. Okay, you don't need to do it part by part. Just you can, until this u n becomes 0, one of this becomes 0, you can continue. Okay, so plus minus will alter. Okay, do you understand this one? This is a very useful one in the case of Fourier series. This is a very important one. Important in the sense that very useful one. Do you understand, students? Tell me whether you understand. Now none of you are talking. Only if you are responding. Hello, do you understand? Right, fine. So I will upload this writing pad also. So I will upload today's video also. If possible, I will have one lecture tomorrow on integral transform and we can finish it. Because actually I plan to, because only we have 2 pages. Okay, we have only 2 pages. So I just supposed to finish it today, but time, time does not support us. Anyway, we need another session, and I think we can finish it within 1 hour. But I am thinking of giving a summary. Summary means so give a big picture on Fourier transform, because we are using a lot of formula and there are different versions. So better give a summary also. So if possible, tomorrow night or sometime morning, I will depending on my situation, I will send you the link. So this week, sometime it may be Friday. So this week we are finishing this integral transform. Okay, then we are moving to real analysis. Here actually the inverse of this one. So actually inverse also we have to work out. So I will ask tomorrow